The next type of application problem we are going to work on is something called an incline problem. So I'm going to jump straight to example 8 and read through the problem so you have an idea of what an incline problem is. So example 8 says find the force required to keep a 2,500-pound car parked on a hill that makes a 12-degree angle with the horizontal. Okay. So this pretty much explains what an incline problem is. You have some kind of object. Here it's the car. It's parked on an incline. So here that's the hill. And when you think about a car being parked on a hill, there is some force that is required to keep that car in place so that it doesn't roll down the hill. So the goal here is to find that force that is required to keep the car from rolling down the hill. Okay, so that's what we're going to be doing here. Okay, um, when you're solving an incline problem, there's something you should know about weight. Okay, weight is a force. Okay, so we talk about weight every day. We, can step on a scale. We know how much each of us weighs, but we probably don't think about it as a force. Okay, so if you read up here, weight is a force, which means it's a vector because force is a vector. Its direction is always straight down. That is towards the center of the earth. Okay, so if you think about if you just stand in place somewhere, your weight is a force that's acting straight down, meaning it's towards the center of the earth. So that's something you have to know, that weight is a force vector and it acts straight down. When you do these incline problems, you will always be given the weight of the object and you're going to have to incorporate that in your solution. Okay, it's very important to the solution process. Okay, so now that we know that, let's revisit example 8 and talk about how to solve it. So again, we're finding the force required to keep a 2,500-pound car parked on a hill that makes a 12-degree angle with the horizontal. Okay, we're told to round our answer to the nearest pound. We're solving for a force, and so pound is 1 unit of measurement for force. Okay, when you do these incline problems, you absolutely have to draw a picture. That is a must. Okay, so I'm basically going to draw a car parked on a hill. Okay, so I am first going to put the ground. Okay, so I need to put the ground on here. So maybe right here. Okay, and then I'm going to draw an incline. And I'm told for this problem that the incline is 12 degrees. That's kind of a tiny angle. I'm going to exaggerate it just so I can draw on the picture. So I'll go ahead and say, all right, the incline looks like this. So again, this is greatly exaggerated, but I'm saying that this is a 12-degree angle. And we know that there is a car parked on the hill. Okay, I am going to treat the car as a single point. Okay, so there's the car. And we know that the weight of this car is 2,500 pounds. Okay, so what we just said is that weight is a force, which means it's a vector, and it acts straight down. Okay, so we're going to draw the weight vector here. Okay, and it will go straight down. Okay, like this. Okay, it is a vector, so you have to put a direction on it, and again, that is straight down. Since this thing is drawn straight down, that means this is a right angle, and that means this is a right angle. Okay, now we know the weight is 2,500. That is the magnitude of this force vector. Okay, so we know the magnitude here is 2,500. We can go ahead and label that. Okay, so what are we trying to find here? Okay, we are trying to find the force required to keep this car parked on the hill. Okay, so if you think about the car being parked on the hill, so here's a car and we're trying to keep it from rolling backwards. So the force to keep it from rolling backwards has to act in this direction. So in terms of our picture, this is how we're going to put it on the picture. Okay, so it's going to work like this, like right here. Okay, it's going to act in this direction. So this is the force vector F. I'm just going to call it F for force. That's what I'm trying to find here. Okay, I'm trying to find the magnitude of this force. So let me write that down. The goal of this problem is to find the magnitude of force vector F. Okay, All right, so let me erase this. Okay, now that we know what we're looking for. Okay. All right, so this is the basic setup. Okay, this is the picture you should come up with. Okay, so now we basically have to work the picture to figure out the answer. Okay, again, we're trying to find the magnitude of this red vector. Okay, I am going to start by looking at the triangle that we see in the picture. Okay, so let me shade it in. I'm going to look at this yellow triangle and see what information it provides us. This is a right triangle because when we drew the weight vector straight down, that created the right angle. So we know that there's a 90-degree angle in this triangle. We know there's a 12-degree triangle, 12-degree angle in this triangle. So we can figure out the measure of this angle right here. Okay, so there's 180 degrees in a triangle. Take out the right angle, that leaves us 90 degrees to spare. Take out the 12-degree angle, that means this other angle is 78 degrees. Okay. All right, so I'm going to start there. Okay, now comes bit of the tricky part. Okay, so I am going to create a box. Okay, so I'm going to create a box such that this force vector is one of the diagonals of the box. Okay, and this is how I'm going to draw it. I'm going to start here and I'm going to draw this way such that this is a right angle. Okay, and like I said, I'm making a box. Okay, so if I want a box here, I want this side to be parallel to this side. Okay, and then I want this side to be parallel to this side. Okay, so let me finish drawing this. I'm making a box. Okay, so essentially this is a rectangle. Okay, so this is a right angle, this is going to be a right angle, this is a right angle, and then right here, this is a right angle. Okay, so right angle, right angle, right angle, right angle. Okay, I am making a box. I have made this rectangle, and the weight vector is one of the diagonals of this rectangle. Okay, so I'm going to erase this yellow triangle because now we're going to look at something else and shade it in. Okay, this rectangle is a parallelogram. Every rectangle is a parallelogram. I have a pair of parallel lines. This is parallel to this side. This side is parallel to this side. Okay, and we also know, since we're dealing with a rectangle, that this side has to equal this side and this side has to equal this side. Okay, so what happens here is we've got this rectangle and we've got this weight vector drawn in, and that splits the rectangle into two equal triangles. Okay, so this triangle is going to be equal to this triangle. Okay, they are equal. Okay, that's what happens when you have a rectangle and you draw one of the diagonals. It splits it into two equal parts. Okay, so these guys are equal. And now comes a part that you have to remember from like a high school geometry class. Okay, so watch this. Just stick with me. Okay, like I said, these problems are tricky. I am going to extend this line down here. Okay, so this line, the base of this green triangle. Okay, I'm just extending the line so I can see this a little better. Okay, so just making the line longer. So let me do it in the other direction. Give me a second, and then we'll talk about why I'm doing this. Okay, so here we go. I've got this line extended. It's supposed to be a straight line. I'm trying. I think that's a little off. Okay, hold on. Okay, so here we go. We've got this line. Okay, so what's happening here, this line needs to, it is parallel to this line. Okay, so what you should have learned from high school geometry, okay, and I'm going to write it down. If a transversal cuts a pair of parallel lines, then alternate interior angles are equal. Okay, that's something you should have, hopefully you remember from high school geometry. If not, You're refreshing your memory, okay? If a transversal cuts a pair of parallel lines, then alternate interior angles are equal, okay? So I've got my parallel lines. I've marked them with with the double arrows here, okay? Those are the parallel lines. The transversal is a line that cuts them, okay? So there's a couple of transversals here, but I'm thinking about this one, okay? The one associated with the weight vector here, okay? So I'm just extending the line here so we can see this better. Okay, this is a line that cuts this pair of parallel lines. Okay, so what this tells us is that alternate interior angles are equal. Okay, interior means that the angles are on the inside of the pair of parallel lines. Alternate means they're on different sides of the transversal. So if you see this 78-degree angle right here, we know this part of the triangle, this yellow angle right here is 78 degrees, okay? It is inside the pair of parallel lines, okay, so it's an interior angle. If we go across the transversal here and we go to the alternate angle that's also on the inside, that's going to be this angle right here. So this guy is also 78 degrees, okay? So that's what that tells us, okay? In both the yellow triangle and the green triangle, we have a 90-degree angle and we have a 78-degree angle, and we already did a calculation earlier, okay? That means that the remaining angle has to be 12, okay? So let me try to grab a different color here. This has to be a 12-degree angle, okay? This has to be a 12-degree angle. Okay, so now we've got this with these two triangles. Okay, we've got all the angles labeled. Okay, and we know the magnitude of the hypotenuse of both of these triangles is 2,500. Okay, so you're probably like, why in the world is she doing this? Well, just stick with me, okay? So here we go. What can we do now? Okay, well, we can now figure out this side right here that I'm highlighting in red. Big hint, I'm highlighting this in red. What else is highlighted in red? Okay, I need to try to figure out this side. Okay, or the magnitude of this vector. I'm gonna call it x. Okay, so when I look at this, okay, what information can I use to do this? Well, if I look at the 12-degree angle and I go across, that's what I'm looking for. This is the opposite side. Okay, and then if I'm looking at the green triangle, if I go across from the hypotenuse, or sorry, if I go across from the right angle, this 2,500 is the hypotenuse. Okay, so I'm going to write down that the sine of 12 degrees is equal to the opposite side, which is x, over the hypotenuse, which is 2,500. Okay, so this is going to allow me to solve for the magnitude or the length of side x. Okay, if we want to solve for x, we need to multiply both sides by 2,500. Okay, so I'm going to multiply this side by 2,500. That way I have one in the top and one in the bottom. They cancel, leaving me with x. If I multiply the right by 2,500, I have to do it to the left side. Okay, so on the right side, 2,500s cancel. I'm going to get that x is equal to 2,500 times the sine of 12 degrees. Okay, I'm going to pop this into my calculator. Make sure you're in degree mode. Okay, so here it comes. Okay, this is the magnitude of that red side that I have labeled x. Okay, so I'm going to write the whole thing down. It is equal to 519.779,227. Okay, so this is basically, this is a magnitude. Okay, so that is the length of this vector that I have labeled x. Okay, so you're probably, again, still saying, why is she doing this? Because I need this force vector F up here and she hasn't even touched it. Okay, well, here we go again. Okay, now I'm going to get to that. Okay, I am going to draw in another line. I am going to connect this point to this point. Okay, so now I'm going to get rid of this yellow here. Okay, and we're going to focus now on this parallelogram made up of the blue triangle and the green triangle. Yay! Okay, so what do we know here? We are dealing with a brand new parallelogram, okay, made up of these two triangles. Okay, so we know that this side has to equal this side, and we know this side has to equal this side. So since I already know x, that means that the force vector that we're looking for has to have the same magnitude. Okay, so not only is this the magnitude of vector x, it's also the magnitude of the vector that we are looking for. Okay, so to answer the question, we need to round to the nearest pound. Okay, so if we do that, after the decimal point, we have a 7, so we need to bump this up to 520. Okay, we're going to say the force that is needed to keep this car from rolling down the hill is approximately 520 pounds. Okay, and I'm going to go ahead and put that this is the magnitude. So I'm going to put the magnitude notation on here, and that is the force that we are looking for.